Okay, we continue with the Fourier series. Remember, we defined the Fourier series for a periodic function. We found the Fourier series for the function x as a periodic function, for the function x squared the same. We learned the Dirichlet-Denise test or theorem about when the Fourier series is equal to the function. We applied that nice result to obtain some sums, like the sum of 1 over n squared, the sum of -1 to the n plus 1, the thing shown here on the screen, the sum of 1 over n squared, the sum of -1 to the n over n squared. So we found all these summations as an application, as a nice application of the Fourier series. Sorry. We continue now with more examples on the Fourier series, and usually when engineers learn the Fourier series, one of maybe the first examples that they solve is what's called the rectangular wave. So what do we mean by the rectangular wave? We mean basically if we take the function, for example, -1 when minus pi is less than x less than 0, and 1 when x is between 0 and pi. And of course, as usual, we extend this function periodically. Okay? So this function is called rectangular wave. Why is it called rectangular wave? Because if you draw the function, so this is minus pi, this is pi. So between minus pi and 0, it's 1, -1, sorry. Then between 0 and pi, it's +1. It's like this. Again, I don't care. We don't care in all applications of the Fourier series. We don't care what happens at the endpoints. Like in this example, do we care if these open circles are not open? Like this point, is it included or not? This point, is it included or not? And why do we not care? We have two reasons. The first reason is that in computations of the Fourier series, in the computations, we have integrals, right? And when we do integrals, points do not matter. So when you integrate, for example, from -pi to pi, is this minus pi or pi included? This is irrelevant. This is nothing, because as you know, the integral represents an area. Let's go back to this idea. So if you're computing the area of this rectangle, for example, do you care if this side or this side are included? We don't. They don't change anything in the area. That's why we don't care. This is the first reason why we don't care about the endpoints. Are they included or not? That's irrelevant. The second reason is whether they are included or not. Remember, in our application of the Dirichlet theorem, because these points at this point, like the 0, the function is not continuous. So in that case, we need to take the average, the limit from left, the limit from right. So whether you include this point or not, the limits are still the same. This doesn't change anything. That's why, again, we don't care what happens at these points. And that's the reason why we don't write anything here. Like, do we say less than or less than or equal? That doesn't change anything. So if you see something equal or not equal, that doesn't change anything. Okay, so this is our function. Usually this function in communication is called rectangular. Why is it called rectangular? Because this is like the basic block between -pi and pi. But then if you extend it periodically, then you just copy what you have and paste, right? So roughly speaking, this is what you're gonna have, like this, and so on. So if you connect these, this is not part of the function, okay? But if you connect them, you see something like rectangles. So this is why it's called rectangular waves or rectangular functions. Okay, so this is again, this is our function. We want as a first part of the example, we want to find the Fourier series of this function. So remember all the time, when we find the Fourier series, we need to find a node, an and bn, according to the formulas we have earlier. The first thing, when you look at this function, just look at the right part, red right part, the left part here, and you can see if you look at the origin as a mirror, you can see that the image of the left part is the right part, or the image of the right part is the left part. So basically my function is odd. So this is the first observation, that f is odd. When the function is odd, when you compute a node, which is 1 over 2 pi integral minus pi to pi f of x dx, the function being odd, this integral is 0. The same for an. When you compute an, this is an. Because the function is odd, the cosine is even, the product of an odd with an even function is odd. Because the integrand is odd, the total integral from negative pi to pi is 0. So basically what's left to compute is just the bn. So what's the bn? The bn is 1 over pi, integral minus pi to pi, f of x sine and x dx. Now because f is odd and sine is odd, their product is even. So let's write this just to make sure we get everything. So this is odd and this is odd. This means that the product is even, and when you integrate an even function from negative pi to pi, it's double from 0 to pi, and between 0 and pi, what's my function? According to the definition, it's 1. So you replace f of x by 1 times sine n x dx. So basically this is my integral. You just do the integral. What's the integral of cosine? Of sine, it's negative cosine over n from 0 to pi. So you have minus 2 over m pi. Then you substitute the pi, that gives you cosine m pi. You substitute the 0, that gives you cosine 0, okay? So this becomes minus 2 over m pi times, what's cosine m pi? Negative 1 to the n as usual, minus 1, okay? So this is the bm formula. Now, when you can stop here, of course. You can stop here. Or instead, you can say, okay, what is minus 1 to the n? Minus 1 to the n could be 1 or negative 1 according to the n values. And remember, the n are integer values. So because it could be 1, that means this term becomes 0, right? Because 1 minus 1. So when is it 1? It's 1 when n is even. So basically, I can say this is negative 2 over m pi times what? It is 0 when n is even, right? If n is 2, 4, 6, this will be 0. But if n is odd, minus 1 to the odd is, so we're talking about this. So minus 1 to the odd is minus 1, minus 1, so that's minus 2. So when n is odd, this will be negative 2. So if you multiply the negative 2 over m pi, this will be 0 when n is even, and it will be 4 over m pi when n is odd. Okay, so this is the bn. Now after finding, so remember, we already found the a node an, which are zeros, and now we found the bn. So basically now we are ready to write our formula for the Fourier series, which is a node, that's 0, plus the sum, and from 1 to infinity, an, that's 0, plus bn, so I'm going to write it, bn, times sine nx. Now in our example, what is the bn? So the bn, when n is even, it's 0. That means when you're running this summation, you're just running over the odd indices, right? So 1 counts, but the 2, the 4, the 6, they don't count. So you're just computing for the odd, and when n is odd, what is the bn? It's 4 over m pi. So this is 4 over m pi times sine nx. Again, we don't like seeing this multi-sub-indices, n is 1, and underneath odd, we like to replace it. So we replace every single n with 2n minus 1, again as a general formula for any odd function. And inside the sign also, the n should be replaced by 2n times x. Sorry. I just have big parentheses. So this is, in the end, this is what we have for our series. Okay, this is the Fourier series. Okay. So again, we started with the rectangular function, the rectangular wave. We found the all Fourier coefficients. Remember, these A's, A0, An, Bn, these are called Fourier coefficients. So in the end, we got this Fourier series. I think I don't need to remind you, but quickly, what does this Fourier series mean? So I'm trying in every single example to remind you of the meaning so that things become familiar, okay? So again, this is not included. We're doing it this way. This is not included. We're doing it this way, and so on, okay? So this is like this, and so on. So again, if you take partial sums, so just imagine you take the first term of the sum, you draw it, the second term, you draw it, the third term, and you add, of course, these terms, the partial sums. In the end, you will see that the partial sums are getting closer and closer. And again, they have the ability to jump these discontinuities. They jump to be very close to the function, okay? I will make one particular video with Mathematica, okay? So I will show you exactly how these Fourier series become very close using Mathematica for all functions that we have done so far, okay? But this is like our hand drawing. Okay, so this is the meaning of the Fourier series. Again, after finding the Fourier series, we can apply the Dirichlet result, the Dirichlet theorem, to find some sums. So for example, here, in this example, so imagine, for example, so this was, remember, the first part. The second part, sorry, need black. Okay, the second part. Let's find, in this example, the sum of -1 to the n over 2n minus 1, and from 1 to infinity, okay? Now, what do we mean by this sum? This sum is exactly -1 plus 1 over 3 minus 1 over 5 plus 1 over 7 and so on. So basically this is the sum again, the alternating sum of the reciprocal of odd numbers. And remember, we found this sum. We found this sum here, it's pi over 4, but we need to be careful. This power here is n plus 1. In our example, it's n, okay? It's n. So we just need to be careful. So we expect the answer here to be negative pi over 4, because in that one, we found it pi over 4. Now we have an extra negative sign, so it will be negative pi over 4, okay? This is our expectation. This is what we expect based on our previous solution, but we need to see the difference. In this example, we are using this function. In the previous example, when we did it the first time, we used the function x, so the two functions give rise to this sum. Okay, so how do we do it? In this example, we have this Fourier series, so I'm going to write it again. So we have the Fourier series as the sum 4 over 2n minus 1 pi sine 2n minus 1x, okay? And please, I don't need to write a bigger bracket here to tell you that the x is in the sum, okay? That's very clear. That's very clear. We would never write it this way unless the x was inside the sign. Okay, so this is the Fourier series. Now the idea is you look at this Fourier series and you compare it with what you want. So you compare these two lines and you ask yourself, what is the appropriate x? What is the x value that after substitution gives me this thing here? So it's very clear that we need to substitute something that gives us minus 1 to the n, right? So for example, if you substitute 0, what do you get? You get sine 0, which is 0. So basically you don't get anything. It becomes the sum of 0, which is 0 clearly. If you substitute pi, you get 0. So the 0, pi, 2 pi, they don't help at all. So what about if you substitute now? So okay, so this is the main idea. So I'm trying to substitute something that gives me alternating signs. So if I substitute pi over 2, what happens? We have the Fourier series of f at pi over 2. Remember, this is equal to f of pi over 2 from right plus f of pi over 2 from left over 2, right? This is the Dirichlet theorem. Now when you substitute it, so from the left side, if you substitute into the series, this becomes the sum 4 over 2n minus 1 pi sine of 2n minus 1 over 2 pi, right? When you replace the x by pi over 2. Now what is f of pi over 2 from right, from left over 2? The pi over 2, in this example, this is the pi over 2, right? So the function, the red function, is continuous at that number. So basically this is equal to f of pi over 2. And what is f of pi over 2 in this example? Because the pi over 2 is between 0 and pi, it will be exactly 1. Okay, so this is just 1. Okay. So this becomes the sum, and from 1 to infinity. If you agree, the pi, these numbers inside the sum, this 4, this pi, these are just numbers, constant. So I can take them to the other side. I can take them to the other side, and we will get 2n minus 1 down. We will get pi over 4 on the other side, right? So what about, so now what's left is only this quantity, the sine quantity. So what's sine 2n minus 1 over 2 pi? You start substituting numbers just to understand the behavior of this quantity. So if you substitute the 1, you get 2n minus 1, which is 1. So you get sine pi over 2. Sine pi over 2 is 1. So when you substitute 1, you get 1. When you substitute 2, you get sine 3 pi over 2. You get negative 1. When you substitute 3, you get 1, 4, negative 1, and so on. So it's clear that the sine gives you minus 1 to a power. Now, is it n? Is it n? It's not, because if you say it's n, then when n is 1, you should get negative 1. When n is 2, you should get 1, and this is violating what we just found. So basically, it's not n, it is n plus 1 or n minus 1. It's the same thing, by the way. Okay, so this is exactly our summation. Okay, so what we found is that the sum of negative 1 to the n plus 1 over 2n minus 1 is pi over 4. Again, this is exactly what we found before, right? This is exactly this. But again, we found it using another function. Now, this is not what we want. What we want is the sum of negative 1 to the n. So how do we make the negative 1 to the n plus 1 equal to the negative 1 to the n? So this is negative 1 to the n over 2n minus 1 multiplied with negative 1 equals pi over 4, right? Because negative 1 is negative 1 to the 1. When you multiply, you add the powers, basically. You get back to the n plus 1. And then, so this is a negative 1. You just multiply both sides with negative 1, and this negative goes to the other side. So now my conclusion is that this sum is negative pi over 4. Again, we expected this from the beginning. So this is again how to apply the Fourier series to find certain sums. We need to be very careful in choosing our x value that gives me what we need in the summation. Okay, so this is this function.